Hey everybody, it is Mr. Blake here, and today we're going to be talking about covalent bonding. I apologize for giving you the lecture in this format. Unfortunately, something's up with the webcam here, so you can't see all the faces I'm making at you, and vice versa, I suppose, right? So it's going to be a little weird with just the voice coming through, so I'll try to be as clear as possible and use some of the drawing features. But we spent yesterday talking about ionic bonding, and we have a little bit of experience with ionic bonding just from doing our nomenclature unit, where we talked about balancing charges and how we have cations and anions, or which are metals and nonmetals, respectively, and how they have to come together in certain ratios. And those ratios represent a much larger three-dimensional structure we call a crystal. And really what it comes down to is one atom in that, or maybe multiple atoms, were so much more electronegative. That is, they attracted electrons so much more to themselves that they stole the electron from another, a weaker, a less electronegative atom. And when they did that, they acquired opposite charges, which allowed them to stick together like magnets. Now we're going to talk about covalent bonding. And the only thing we've said prior to this is that covalent bonding occurs between two nonmetals. You might remember it is a sharing of electrons. All right. And so whenever we see a covalent bond, we need to understand that there's actually two electrons accounted for. One, in most cases anyway, one coming from each of the atoms involved in the bond. So um, what happens in a covalent type of bond situation with regards to electronegativity is that neither of them, they're basically trying to steal each other's electrons, but neither of them is stronger than the other. And so because of this, we tend to find covalent bonds occurring between atoms that have similar electronegativities. You'll see in the video here, and I want you to take note in the crash course video that I put on Edpuzzle, that there's a definite range, and typically we consider anything with a difference in electronegativity of 2 or more. So we know that the highest you can get is 4, and that's fluorine. That has the highest electronegativity, and that the lowest electronegativity is about 0.7 down on the lower left portion of the periodic table, like cesium. So knowing that every element, if you look on a periodic table, has a small number written down, and I believe it's in the upper right-hand corner of your periodic tables. If you see that it's 2 or greater, we are dealing with an ionic bond. Really, anything less than that is covalent. And if they're the same, it's what we call a pure polar covalent, which is sort of like imagine two electrons, and they're both, and two atoms are fighting for it, but it's like a tug of war between identical twins. So things like all the Hofbrinkels, right? Hydrogen and oxygen and fluorine and chlorine, they form covalent bonds, but they're trying to steal each other's electrons, but they're 100% identical. It's two of the same atom trying to steal from one another, and so they end up sharing it very evenly, right? Molecules, or I guess we'd say compounds, that are created by covalent bonding we call molecules. So we use the word molecule a lot, but sometimes inappropriately, because it should really only apply to things that are held together by covalent bonds. All right. Okay, so what do we have some properties? We talked about our properties of ionic compounds yesterday. What about molecular compounds? First, they're a lot weaker. You can see them. They form gases. They form liquids, softer solids, whereas the ionic compounds we know form crystals that have really high melting and boiling points. So we're going to see, because of this, these bonds being a little bit weaker, they're a little easier to separate. So they're easier to melt. They're easier to make them boil. Those two things tend to go hand in hand. And unlike ionic compounds, which are really only solids at room temperature, these guys can be pretty much anything. You run the whole gamut. So you get a lot more variety with these covalent compounds. It also makes up all of organic chemistry, which is us, essentially. We are held together by covalent bonds. We are not crystals, right? So it adds, even though it seems like it's a little weaker, it actually has a lot more diversity. And they don't conduct electricity in any state. So it doesn't matter if you dissolve them, doesn't matter what you do to them, they are not going to be able to conduct electricity for you. All right? So some properties, a few more. The formula that you get is, unlike ionic compounds where it's representative of a ratio, this is actually, the molecular formula is the true formula, the exact makeup of one individual molecule. So if I'm talking about a water molecule, it is two hydrogens and one oxygen, and that is its own thing. That H2O is its own thing. It can be separate from others. Whereas if I did sodium chloride for an ionic compound, it would be very much part of a much larger structure. Right? So here's an example. This is glucose. This is pretty much what makes your body, this is the fuel that your body uses to generate most of its ATP. And when we see C6H12O6, if that were an ionic compound, we would reduce that to CH2O because you divide all those by 6. It's not in the lowest ratio form, right? But that is, in fact, what glucose is. It's a ring structure you can see there, and that is its exact makeup, CH12O6. Okay, so kind of going into this idea here of sharing electrons and that these occur between nonmetals. And remember, hydrogen, which is in group 1, but is actually capable, is still technically considered a nonmetal. So it gets its own thing. Not everything in group 1, but just hydrogen has 1 valence electron. Everything in group 14 has 4, 15 has 5, 16 has 6, 17 has 7. And so what that tells you is not what charge it will make in this case, although these guys, as you know, you've seen plenty of examples where they do make charges when they're combined with metals. But what if they bump into each other? All right, well, here's what happens when you put these nonmetals together. Each of them are a few electrons short. Hydrogen is a weird one because it only needs 2 to get its valence shell full. Remember, that first energy level only has a sub-level, so it can only hold 2. So that's all hydrogen needs. So it needs 1 more electron. Everything in group 14 has 4 valence electrons. Now, that means it's going to need exactly 4 more to get to 8. Group 15 has 5, so it's looking to pick up 3 more. Group 16 has 6, it needs 2 more. And group 17 has 7. That's the greediest of them all because it only needs 1 more. It's really, really close to getting what it needs. So for hydrogen, because it only needs 1 electron, it only needs to share once. So hydrogen will only make a single bond. You will never see hydrogen forming 2 bonds in the same molecule. It's not even possible. Whereas something like carbon in group 14, the reason why carbon is so amazing and so diverse, in fact it has its own branch of chemistry, is because of the many, many ways in which it can bond. Carbon can form up to 4 bonds because it needs 4 more electrons. Everything in group 15 needs 3 electrons, so it can form up to 3 bonds. And group 16 can form 2, and of course group 17 can form a single bond. That's what they like to do. That is their most stable bonding configuration. So let's just show you kind of how this looks. We're going to start out pretty simple. There's 3 things we want you to do. First is the rough copy, which is just sort of your scratch work, really. Then we're going to use the dot formula to show how these things would bond up, and then we'll use the Lewis structural formula, which is named after a really famous chemist named Gilbert Lewis. And we'll do more work on that in class, actually. I'll give you a lot more examples. So this is pretty basic stuff here. All right, so let's say we have hydrogen and another hydrogen. All right, so you got these 2 hydrogen atoms, and they each need 1 electron. And they look at each other and they say, hey, you have an electron. And the other one looks at it and says, hey, you have an electron. Well, again, they don't have feelings. They don't make decisions. They're atoms. So what they essentially try to do is there's an attraction to each other's electrons. Okay, from the opposite one's protons, the opposite one's nucleus. So they pull each other in towards themselves, and what happens is these electrons right here end up getting split. Okay, so they will end up being shared. Basically, I like to think of this really simple as like a joint checking account. My wife and I each have put money into the account, or at least we used to. But when we were doing that, if you had asked her, let's say we had $20,000 in the bank. I'm making a really large sum up. We never had that much money in the bank. But let's say we had $20,000 in the bank. Now, I contribute to that through my paycheck, and she contributes to that with her paycheck. But did each of us have individually $20,000? Of course not, right? Now, but did each of us have access to $20,000? Yes, we did. So if you're looking at hydrogen, remember, needs just 2 electrons. Well, it has each of them, if they share it, if those electrons hang out in between, have access to those 2 electrons. So each of them has become stable because they can access those 2 electrons, and they're happy. But that happiness only lasts as long as they are together. And that is a bond. And when we draw the Lewis structure, what we do is we take those double dots in the dot formula and we replace them with a line. Okay? So a single bond is going to be represented by a single line. Right? So whether it's a double dot or a dash like you see there, it's all going to be the same. The dash represents 2 electrons. Sorry if you can hear one of my pugs barking in the background. The next one we're looking at is O2. Okay, so oxygen, and I apologize here, I moved this to a full screen format and the formatting got a little messed up. I couldn't undo it quickly. So there is in fact a little dot just underneath the oxygen. Let me see if I can find it here. I'll put it in green. There's that dot right there. Okay, and then the next one, okay, the next one that we're going to do here is, sorry, I'll have to clear it. So write that dot in down there. That gives it its 6th electron. You can kind of see it peeking out on through the O there. The next guy, forgot that was on. You can see another one there. And again, if you want, I'm not going to risk that one again. Draw a little dot underneath that. So each of those you can see have 2 open spaces because the oxygen needs 2. So what we do is we have one there, and we have one right there. And let's see if we can work this out here. We are going to put these guys in here. So right here, we got a dot, and here we have a dot. Okay, so now there are 2 bonds there being shared, right? 2 bonds, okay, in the dot formula. And you can see there's a total of 4 electrons, or 2 pairs of electrons, however you want to think about it. You should probably think about it in both ways, actually, being shared there. So if you look around the oxygen, and let's go ahead, we'll write it here. Let's go back and look at that dot formula, though. So if you look at the oxygen on the left here, it has access to all 8 electrons. And if you look at this oxygen, also full access to all 8 electrons. So together, as long as they're close, as long as they're being held together like this, each of them has that octet that they were looking for. Again, there's going to be 2 dashes, and that is how we will demonstrate that there's what we call a double bond. All right. Now the rest of them we call unshared pairs, which means that they are just kind of hanging out. Each of them belongs to those individual oxygens, and it's going to form a covalent bond between the 2 nitrogen atoms. Each of those nitrogen atoms have 5 valence electrons. That means each of them is looking to get 3 more. Now nitrogen will form ionic bonds if you put it with a metal. If you put it with something with a way lower electronegativity, it can take electrons from less electronegative metals, like potassium especially. But in this case, if you put 2 of the identical atoms together, neither of them is strong enough to take, in fact, they're equal strength when it comes to electronegativity, neither can take the electrons that they need from the other. So they do what atoms do, and that's they share. Again, this isn't a choice. This is just simply physics here. These guys are trying to take the electrons, but it's a lower energy configuration for them to share them than it is to try to take them. So if you look, those 3 unshared electrons right there are going to be the ones that end up getting split between them. And so we have sort of that joint checking account situation where each of them is contributing an equal number of electrons so that they can share all of them. So if you look at the nitrogen on the left, it has access to the 8 electrons. If you look at the nitrogen on the right, it also has access to the 8 electrons. And each of them is happy, okay, as long as they stay together. This is, again, similar to a marriage. Each party brings in some cash. Each party has access to it, but you better stay together, otherwise your economic stability will go down the drain. Unless your wife quits her job, in which case you are the sole money maker, and then, just do your thing, I guess. My wife is right here, sorry. Okay, so that was a triple bond. Let's do something where we're not looking at the same atom. The first thing that we're going to do, we're going to look at still something pretty simple and really common, water. All right, so here is water. I don't really care how you set this up. I have it set up on an angle for a reason that will become apparent later. But there is a decision when you're not dealing with diatomic elements like nitrogen and oxygen and any of the Hofbrinkels where you have different atoms involved, different elements involved. There's this question of I need to put a central atom in there. Which one should it be? Which atom goes in the middle? And typically, the one that makes the most bonds, and if you go back to that chart you just filled out, it'll tell you based on its group number which one likes to make the most bonds, or which one is the least electronegative. Those are the ones that tend to go towards the middle. So I like that first way of thinking about it because it usually works with most. So let's look, we put oxygen in the middle and we have hydrogen there, and we write their electron dot structures just based on their number of valence electrons. Well, you can see oxygen and hydrogen will share two different bonds. Now this isn't a double bond, this is two separate single bonds that occur because they're between different outer atoms. So the hydrogens are considered the outer atoms, and that oxygen we would call the central atom. And so if you look at this picture right here, the oxygen has 8 valence electrons around it, and the hydrogens each have 2. Now again, you might think, well, where are the rest of the dots around hydrogen? You got to remember, hydrogen is sort of that rare exception. It can only form a single bond. It will not have any other valence electrons around it. It is totally stable with 2 electrons. So it's a little bit of an exception to our normal octet rule. Right? When I transfer those shared pairs of electrons into the Lewis structural formula, remember we're going to replace those double dots with dashes. And so that's what it looks like. You have 2 bonds, and then you have 2 unshared pairs on that oxygen atom. All right, last one, ONF here. So we have oxygen, nitrogen, and fluorine. And again, I got to decide which one should go in the middle. So let's use the rule that you just put in a minute ago, and that is which one of these likes to form the most bonds. Well, we know oxygen has 2 spots for a bond, fluorine has 1 spot for a bond, whereas nitrogen has 5 spots. So the big winner there is nitrogen. So we put that in the middle. As far as oxygen and fluorine go, doesn't really matter. You can put them on either side. All right, so let's look here. Nitrogen wants to form 3 bonds. So it's going to form a single bond with the oxygen. It'll form another bond with the oxygen. And then you have that single bond with the fluorine. When that happens, let's condense this now into our dot formula. And you can see you have the 2 shared pairs between the oxygen and nitrogen, 1 shared pair between the nitrogen and the fluorine. And then we translate that to our Lewis structure where we replace those double dots with a dash, and that is your formula. And we're going to do a lot with these in the upcoming week, but you need to be able to make sure that you can draw these really simple structures. We're not talking about shape, we're not talking about polarity or anything that becomes pretty important later on down the road. Right now, we're just focused on which one goes in the middle. Are they double or single bonds? How are these things put together? All right. So make sure you look at the crash course that I posted on Edpuzzle, and there's some extra good information, especially when it comes to those electronegativity differences. I expect you to be accountable to those for that information because it may show up in your test. All right. Have a good day.